Here is a physics question that someone asked me. Can you fall faster than terminal velocity? And the answer is yes. Spoiler alert, the answer is yes. Can you fall faster than the speed of sound? We'll find out. Okay, so I'm going to start off with, so there's a picture, it's a plane, it has nothing to do with falling except there's a cloud, and that made me think of falling, but I actually do have this. This is a video from 1991, and this is me skydiving. I'm the guy in the front. There's a tandem skydive. It has nothing really to do with this except for skydiving. I just wanted to show you that I am a real human and that I did something. And I found this video. You know, I like to have old videos, and sometimes you actually get to use them. So there's me. I didn't die with my jump instructor jumping in tandem. The end. And I do have hair there, even though it's covered up with a little cloth helmet. Let's think about something similar to skydiving, and that's dropping of a coffee filter. So I wanted to drop this coffee filter from the moment I released it, but I released it off frame. So here's a picture of me dropping a coffee filter, and imagine I just let it go. The coffee filters are really nice because they one, have a very large surface area compared to their mass, and so they don't have a constant acceleration when they're falling like a lot of other things. And two, they have a constant shape, and you can actually change the mass by stacking filters, and it doesn't change their aerodynamic properties. But let's say I let it go right away. It's not moving. I just let it go. So there's the downward gravitational force on that. So if we use Newton's second law, it says that the net force, which is only the gravitational force, is equal to mass times acceleration, and acceleration is defined as the change in velocity over the change in time. If I take a very short time interval, then I can assume this acceleration is constant, and I can find the change in velocity at the end of that time interval, v2 minus v1, is delta t. And if I solve this for v2, I get this. So this says that after that short time interval, I can find the final velocity. But more importantly, it's moving. So now that it's moving, I have to consider the effects of air resistance. So let's just look at what would happen if I do drop this coffee filter, and you can see what happens. So here we go. That's pretty awesome, huh? Not very exciting. But it didn't fall like a normal object. I think that's clear. And so how do we model things that fall with air resistance? So the first thing we need to do is consider air resistance. So I wanted to, this is my dog, one of our dogs, and the car is parked, okay? But dogs like to stick their head out of the car windows. And you could do something like this. You could stick your hand out of a car window while it's moving, and you can feel the air pushing on your hand. So a couple things that you should notice about this air resistance force as you drive in a car. Be careful, don't hit anything with your hand. One, that air pushes backwards. So if you're moving in the forward direction, the air is pushing in the opposite direction. So it's the opposite direction as your motion. Second, it depends on your speed. The faster you go, the greater that air pushes against your hand. It depends on the size of your hand. If you take your hand put it in a fist or have it open-handed, the air resistance is different. It depends on the shape of the object. If you had a cone versus a circle, flat circle, those two would have different air resistances. And finally, it depends on the density of air. If we put all this together as a model, it looks like this. This says the air drag is equal to the minus there means it's in the opposite direction of the velocity. We have the velocity is the magnitude of the velocity. Since velocity is a vector, I have to take the magnitude of it. The A is the size of the object. The C is the drag coefficient depending on the shape of the object. And then rho is the density of air, which is 1.2 kilograms per cubic meter on the surface of the Earth. For the most part, changes a little bit. And V hat, that last thing on there, is just a unit vector to make this whole thing back into a vector since I took the magnitude of the vector. Okay, so that's the air resistance force. Now let's look at that for the falling coffee filter. So right when I let go, I have this, my gravitational force pulling down on the coffee filter. It's not moving though, so there's no air drag force. And that's going to make it speed up. So a little bit later, it's moving. I picked some velocity of negative 0.1 in the y direction. And there is an air resistance force, but it's not as big as the gravitational force, so the net force is still down and it speeds up. But eventually it will get down to something like this. where the air resistance force is equal to the gravitational force. And if I add those two together, I get a vector of 0. At this point, the acceleration is 0, and we say this is the terminal velocity. So terminal velocity is that part when the air resistance force is equal to the weight. Okay, so let's not do coffee filters. Let's talk about skydivers. So here's a skydiver. I found this video online on NASA or the government site. So that this is just an example of a skydiver. This is some Ambassador Ronald Johnson. He was skydiving. I didn't have a video of me skydiving because this is 1991. No one had a GoPro, right? Imagine how big those video cameras were. You're lucky I even have a video at all from 1991. I'm just letting you know. Okay. So let's think about this skydiver at terminal velocity. So he's already jumped out of the plane. He's moving down. There's a downward gravitational force, and there's an upward air resistance force, and the net force is equal to 0. And what we want to do is try to get some parameters for how this guy falls so that we can use it for different skydiving jumps. So if I look at this just in the y direction, this has a net force of 0 in the y direction, and the forces in the y direction are the air resistance in the positive y direction because he's moving down, and the gravitational force in the negative y direction, and those have to add up to 0. So let's assume that a skydiver falls with a terminal velocity of about 120 miles per hour. That's a number I remember. Okay. And so if you convert that to meters per second, it's 54 meters per second. And a mass of a skydiver, typical human mass, around 70 kilograms. So I know those two values. What I can do is put those in and solve for the AC term in the air resistance. I don't know the area of a human, and I don't know the drag coefficient, and I don't care, right? I can change the density of air, I can change the velocity, but AC I'm just going to assume are constant values that I don't really even care about separating. So now if I take a skydiver really high, I can assume it has that same AC value. So if you solve for AC in the equation to the left, I get 2 mg over the density of air times the terminal velocity squared, which I know the terminal velocity. And if you put it into the values, you get 0.392 square meters. C as a coefficient doesn't have any parameters. So now let's take it to the next level. Here is the next level. This is the Red Bull Stratos jump from 2012. So this is Felix Baumgartner. He took a balloon ride up into the atmosphere. I think it was 39 kilometers above the surface of the Earth. And when he jumped out, according to the data they collected, he went 1.25 times the speed of sound. And the key thing here, though, you got to think about, at that altitude, the density of air is very low. So if we want to model this motion, which I do, and I'm going to, and you're going to watch me, I do have to take into account the change in density of the air. What about the change in the gravitational field? Do I need to take that into account too, because it's much higher? So let's think about this in terms of building a numerical model to do this, because it's not easy, right? It's not easy to model a skydiver because you have that non-constant air drag force. And now you add in a change in density and maybe a change in gravitational force. This is a complicated problem. So we're going to do this numerically. To build a numerical model, we have to think of what happens. So I already said this actually, as the skydiver falls, the speed of the skydiver increases. As the speed increases, the air drag increases since it depends on the speed. As the air drag increases, the net force decreases. And as the net force decreases, the change in speed decreases. So you see the problem that we have here. And then we have the problem with the density of air. Okay, that changes too. So that just makes it even more complicated, but not really that much more. It's already complicated enough. So let's look at this first question about the gravitational field. Do we have to worry about the gravitational field? So here's the altitude of 39 kilometers. The radius of the Earth is 6 million meters. The mass of the Earth is 6 times 10 to the 24th. I'm rounding. You can see the numbers there. And the universal gravitational constant is 6.67 times 10 to the negative 11th. So I can use that and calculate the gravitational field at 39 kilometers and compare it to the gravitational field on the surface of the Earth is 9.8 newtons per kilogram. So all I need to do is to put in my values for the gravitational field using universal gravity, and I get g times the mass of the Earth divided by the distance between the Earth and the object squared. So that's going to be the radius of the Earth plus the altitude of 39 kilometers, and I get 9.69 newtons per kilogram. So yeah, it is lower. But I just don't think it's that big of a deal. I'm not even going to worry about that. We can do it. You can add that in as homework, but I'm going to assume the gravitational field's constant just because that's what I want to do. And no one can stop me. So here's how we're going to do this. Here's my numerical recipe. Number one, I should have put this as bullet points, and I didn't. It's my fault. Break the motion into small time steps. And then during each of these time steps, I can assume that the force is constant even though it's not. But if the time step's small enough, it works, right? I just have a lot more calculations. So the first step is to calculate that total force. And this is the equation that we've been using with the gravitational force and the air resistance force. Use that force to update the velocity. This comes straight from the definition of the acceleration. Instead of a, I have F net over m, which is the acceleration. And just as a note, I normally do this with momentum principle, but since the air resistance depends on the velocity, I'm using Newton's second law just to make it look a little bit easier. Next, we're going to use that velocity to update the position. I'm using r for the position, and in this case, I'm using the velocity at the end of the time interval to find the new position. And that's wrong. Okay. But like I said before, if delta t is small enough, it's only kind of wrong. And then now that I have the new position, I need to calculate the new density of air, and then I can redo everything. And I can model this motion. How do we find the density of air? So this is straight from Wikipedia. If you just Google Wikipedia density of air, it has this very nice model down here at the bottom. This says that the density of air depends on the pressure, the molar mass, the ideal gas constant, the temperature, and then the temperature depends on this other stuff, the gravitational field and this temperature lapse rate. So, but I have all these values, so I can put all these values into Python and calculate the density at each altitude, and then I can get it to work. Now this says, okay, this is only valid inside the troposphere, no more than 18 kilometers above the surface of the Earth and lower away from the equator. So it's not exactly right, but I'm going to do it anyway. We can make it just a rough proof of concept. We can make something more complicated later, since I'm going to go almost twice that high. So okay, so here's what the stuff that we need to do. Number one is to create a density function for the as a function of altitude, and just do that just to make sure that density calculation works. And then plot the density as a function of altitude. After that, I want to make a Python function of density so that I don't have to redo those calculations every time I use it. I can just do something simple. So if you haven't made a function in Python, that's fine. I'm going to show you how to do it. It's not a big deal. What about the speed of sound? The speed of sound actually depends on the temperature, but the temperature changes with altitude. So we're going to build that. I want to make a plot of speed of sound versus the speed of the skydiver, and both of those versus time, right? So we can see, does he go faster than the speed of sound? Does he go faster than the terminal velocity? Why don't I write that as terminal speed? Okay, so here is the calculation for the speed of sound. I left off the units where T here is the temperature, and we can get that temperature from the density function that we calculated before, and then solving for the terminal velocity as a function of density, right? AC is constant, M's constant, G is mostly constant, but as the density changes, the terminal velocity changes. So this is all the stuff that we're going to do. Let's get to it right now. Yep. Okay, so let's move over to Python and do that stuff over there. So I got a little jump start here. I started with my Python. I put in my constants there. I don't want to put the units because I'm doing a numerical calculation. I'm actually calculating the numbers. So I'm just going to follow the exact same script that we had in Wikipedia. So this says first calculate the temperature. So T equals T0 minus L times H. That was straight from there. Okay. And so L is a constant, T0 is a constant from up above. Next, I'm going to calculate the pressure. P equals, and this is straight from Wikipedia, P0 times 1 minus L times H divided by T0. All of that raised to the power, so raised to the power in Python is star star of G times M, the molar mass, divided by R times L. I think that's it. And then that's then the density, rho, would be equal to P times M divided by R times T. So let's just try that. So let's say if my H is my altitude. So let's say H equals 1 meter. H equals 1, print rho. Let's just print the density. Something happened. P0, 1 minus L times H divided by T0 raised to the G, M, I'm just checking, R over L. What did I do wrong? Let's see. Oh, I know. H equals 1. I use H down there. Okay. There. 1.2. So that's why I said 1.2 kilograms per cubic meter. That's the surface of the Earth. It seems like it's working. Okay. So now let's make a graph. Let's just make sure this whole thing is working. So I'm going to say T graph, that's just the name, equals graph. The X title is equal to altitude in meters. And the Y title is density. I shouldn't even put the units because it doesn't really matter. Kilograms per meter cubed, but I do want to. And then I need the graph to plot. F1 equals G curve. Let's just leave it as that. Okay. So then I'm going to say, let's say, so H equals 0, DH equals 10, and then I'm going to make a loop. So I'm going to say while H is less than, let's say, 20 kilometers. Let's do 39. So 39 E3 kilometers. Then I'm going to do all of this stuff. I'm going to calculate the pressure, the temperature. No, those are all constants. I don't need to do that. Let's type this up here. I don't have to redo that every time. I do need to do this every time. So let's just cut this up. Let's just indent this, indent this, indent that. And then I'm going to plot the density. So I'm going to say F1.plot H rho. Now I'm going to increase H. H equals H plus DH. And that should be set. I don't need to print it anymore. Okay, let's run that. I didn't save it. Okay, but it looks like it's working, right? So this shows that as the altitude increases, the density gets down to essentially nothing. And so we're all cool. But again, I don't want to do all this every time. I want to instead make a function. So let's do this. Up here, I'm going to say def rho. And so this is going to make a function, and I want to input the height. And I'm going to actually call this HH, just so I don't confuse it with the other H. HH is the variable I put in, and then this is going to return the density. So I'm going to put all this stuff, tab it in, indent it so that it's in part of the function, not that. And then I'm going to cut this stuff and put that in the function. And then I'm not going to calculate rho, I'm just going to return rho. So I'm going to return this value. So what this does is it goes through and, I need to do HH. This needs to be HH. That's fine. So this is going to take that value of H, it's going to use it to calculate all this stuff and return this value. So this is really nice. Let me just get rid of, let's just get rid of this for a second. I just want to show you how awesome this is. So if I say H equals, this is print rho of 100. So this will print the density at 100 meters. And 1 point, so it's a little bit less. So that seems like it's working. Okay, so now in the loop, I can turn my loop back on. I'm going to do the same thing. But now, all I have to do is, instead of printing, I don't need to calculate rho separately. I can just say rho of H. Okay, and now I should get the same thing, hopefully. Yeah, okay, cool. So that's our function that we're going to use right there, and that works. So now we can jump right over, and let's open up a new tab so that I don't have to lose this, and let's do what we were doing. So trinket.io, new trinket, glow script, Python, skydiver jump 1. Why does it 1? I don't know. So let's start calculating. Let's just go ahead and put that function in there. So let me get my function. I just already had it, didn't I? No. Let me copy it over here. I want this whole function. Actually, I need this too. Okay, now I'm going to plot, let's plot the speed as a function of time. So this is going to be, darn it. So X title is going to be time in seconds. And the Y title is going to be equal to speed in meters per second. And then F1 is going to be, let's make this blue. And let's give this a label of skydiver. And then we can add in later the other stuff. So down here, I need a couple other parameters. I already have, let's go ahead and put G. Oh, G's in there twice, but that's fine. I think it'll work. I shouldn't have done that, but there's G. Now I need the mass, M equals 70. I need AC was, what was it, 0.3? I can't remember what it was. What was it? It was 0.392. 0.392. I need the initial velocity, V equals 0. I need H equals 39 E3. Yeah, we're going the whole time. We're going the whole way. Okay. I think that's fine. So I'm going to say while, let's just do it for while t is less than 20. I like to do this first as just a time-based thing because if I get something wrong, I'm pretty sure it'll stop. Now, in a lot of other programs, my next statement was rate. The rate is how fast things are visually displayed, but I'm not making a visual animation here. I'm just plotting things. So I want it to go as fast as I can. I don't need the rate in there. But the first thing I'm going to do is calculate the force. So I'm going to do this in one line. I'm going to say F, oh, aha. Okay, I'm going to change this. G, I'm going to call this GG. Down here, I'm going to call this GG. That's fine. So then I can call this G equals vector 0, negative 9.8, 0. And then I'm going to say the velocity is vector 0, 0, 0. And I need the position R. Let's see, let's do that right down here. R equals vector 0, H, 0. And I'm doing this as a vector just because I'm just trying to be a good person, do the right thing. So now the force is going to be M times G. M is a scalar, G is a vector, so that's fine. Minus 0.5 times rho of R dot Y. Right, so R dot Y is my height. The R is my position, but I'm going to put in just the height of my position, which is the Y component. So R dot Y is the Y component, and that is a function rho. Okay, so then I need to multiply that times AC, which is just one thing. And then I need to multiply that by the magnitude of the velocity squared. So it's going to be mag V squared. Now that's not a vector. I need to make it a vector. So I can say multiply it by norm V, which is a unit vector for V. So that looks terrible, but it's not bad. Now the next step, so I calculate the force. The next step is to update the velocity. So V equals V plus F times dt divided by M. So that's what we said before. Now in Python, this is V at the beginning of the time interval, and that's at the end. So it really just updates that value for V. I don't have to have a whole bunch of different velocity values. It looks weird, but it's not actually weird. Now I need to update the position. R equals R plus v times dt, and that's the velocity at the end of the time interval because I just calculated it. Now I could update the time. T equals t plus dt. Oh, and yeah, I did calculate that. Okay, so I think that's right. So now let's do, let's plot f1 dot plot t and magnitude of v. I think that's going to work. You know, I think it's going to work, but I also have this feeling in the back of my head that I made a mistake, and I don't know why, but let's just see. Yep. Line 30. Aha. I never said what t was. T equals 0, dt equals 0. I think if I do it, let's just do 0.01 for right now. I think I might be able to use something bigger than that. But let's see. Look at that. Okay, I think I'm pretty happy, right? Because, oh, it looks like it just keeps speeding up. It keeps speeding up because it only fell for 18 seconds, 20 seconds. And in that area, the density of air is so incredibly small, this is exactly what I'd expect. Let's just jump in here and say while r dot y is greater than, let's say 5,000. So he's going to, at 5,000 feet, maybe he'd pull his parachute, which is pretty high. Let's do 3,000. That's still pretty high, but okay, for a skydiver, based on my vast skydiving experience. So here we go. Run it. I didn't even save it. Okay, I'm pretty happy with that. So look what happens. He increases his speed fairly linearly until about 50 seconds, and then he starts to decrease his speed. So what happens is that he speeds up because the density of air is very, very low. And then once he gets into lower altitudes, the density of air increases, the air drag gets much greater than the gravitational force, and he slows down. And then eventually reaches some nearly constant speed of about 62. And remember, the terminal velocity I used for a falling skydiver was 54. So I'd assume once he gets down to the ground, it'd be 54. Let's do that. Let's do this at 100 meters. 200. I typoed 200. And down here, look at that, 54. He reaches terminal velocity. Okay, I could probably make the time set small. Let's just change this to 0.1. Let's see, this is 414 meters per second. Does that change significantly if I change the time step? No, so I think that's good. It just runs a little bit faster. Okay, so now let's plot the terminal velocity at the same altitude he is at, just as a comparison. So up here, I'm going to say a new graph, f. So because we want to see, does he fall faster than the terminal velocity, which obviously he does. But f2 equals g curve, color equals color dot red, label equals terminal velocity. Okay, so down here I need to calculate the terminal velocity. So let's just do that. Vt equals, what did I say it was? The square root of 2 times m times g. Okay, but now I need to do the mag of g because it's a scalar. Divided by rho of r dot y times AC. And then I'm going to plot f2 dot plot t vt. Let's see if this works. I didn't save it. I'm such a rebel. Okay. Yeah. So you notice up here, it's crazy silly, right? Up here, the terminal velocity is, what is that? 4,800 meters per second, because the density of air is so low. Of course, you never reach that because by the time you start speeding up, you get down here. So you'll see, I want to, let's zoom in on that. So if I do up here, here's a trick. If I put fast equals false and I run it, it uses Plotly to plot this. Now I can highlight this region and zoom in. That looks a little bit better. So here he is falling, and at this point he reaches the terminal velocity at that location, and then he's actually going faster than the terminal velocity, and then he slows down until he gets over there. So that's pretty cool. I'm pretty happy with that. Now let's plot the speed of sound. So we got to calculate the speed of sound, which I got rid of. So let's say Let's just do this as a function. So I'm going to copy this and call this VS for speed of sound. And it's the same stuff, but I don't need to return this. I want to return, I got to look back at my notes, sorry very much for scooching around. It was, I should write this down because I'm going to forget. So it's 331.3 square root of 1 plus t over 273.15. Let's see if we can put that in there. Okay. Where'd I put my bracket? There it is. Okay, so I don't need to return this. I'm just going to put this calculation in here. I'm going to calculate that stuff. It doesn't really matter. So 331.3 times the square root of 1 plus t, which I calculated right there, divided by 273.15. Okay, that might work. So down here, I'm going to plot. Let's not plot F2. Up, I gotta put F3 up here. F3 equals G curve. Color equals color dot green. Label equals speed of sound. Okay. And then down here, I can say F3 dot plot. And I'm plotting versus t, but this is the time, this is the altitude when the guy's at the same time, or girl, whoever's jumping. I was thinking it was Felix. Okay. So now I just need to plot VS, the terminal velocity, the speed of sound at r dot y. I think that's going to work. No, it did not work. Right, line 33. Return, aha. Square root, yeah. Okay. Maybe I should save it. And I'm going to give you the code. Don't worry about it. Check that out. Okay. So you'll notice that the speed of sound increases. Is that right? The speed of sound at sea level is 474. I thought it was 3 something. Speed of sound in meters per second. 334. That's wrong. Okay. So there's something wrong with my speed of sound calculation. I'll have to look into that. Oh, no. Wait. That's it's right over here. But it should be right at the end because he's down lower. Speed of sound increases. Okay, well, I don't want to redo that. And I don't want to, I want to end the video. And this will be your homework. Exactly. But according to this, he does go faster in speed of sound at some point. Right over here, okay, that small time interval, and that is what happened in the actual Red Bull Stratos jump with Felix Baumgartner. But I know there's an error right there, and I'm fine with that. I think this is pretty good. I'm pretty happy with that. So I'm going to leave you the code, and then you can finish things up. But can you fall faster than the terminal velocity? Yes. Can you fall faster than the speed of sound? Yes. And you can model it too. And again, there are some issues here also with the calculations for the density, but it's proof of concept. So there you go. Have fun with this.